Hello everyone, my name is Anthony, and in today's video is going to be a little different. What we're really going to focus on today is the chip selection. Now, when we're creating autonomous drones, the goal is to make the drone see the world 360 vision, like see the world in like a bird. So how are we going to do that? And for that, you need a processor that is capable of computing the world in terms of computer. It's purely through computer vision. So we're looking at designing the quadcopter, or in this particular case, we're designing a quadcopter which would have 6 cameras so that it could see the front, the back, the left, the right, the top and bottom. So it has a 360 view of the world. And we want a processor that is capable of handling all the image inputs, computing it, calculating the depth, and then eventually calculating the navigation patterns, and then sending those signals to the flight controller to move the motors and generate the speed. So we need a processor that can do some form of artificial intelligence, some form of computer vision, and is capable of handling the computational resources. So we have gone so far going to select the S32V processor by NXP, and the goal over here is this particular processor is used mostly for the automotive industry, but we are, the goal over here right now is to take some of these processors that are capable of, that can be used in the automotive industry and in automobiles. We firmly believe it'll probably even work on a drone. Now, the only issue we might have is the amount of power it might consume, but that is something we can optimize later. So for now, we're just really, starting out selecting the chip and the components that might be needed so that we can, start testing our drone as quickly as possible. And the reason why we selected the S32V234 is primarily it's when you're designing this board, there were certain things that caught my attention. One of them is, you could design the board on an 8-layer PCB and you don't need to have 12-layer stacks, which is important because when it comes to fabrication, the more layers, the more expensive it can get. And the less layer, if you can, minimize the layers, at least the minimum layers that you could have in fabricating the PCB, it makes you can drastically save on cost, and the design of the system is also much easier. But beyond that, it's also got the capability of handling 2 MIPI CSI2 connections. So you can virtually connect a couple of more cameras, and I think it would have the capability of handling at least 6 cameras for sure. And it's also got 2 parallel 16-bit camera input. So totally, if you have 4 camera inputs per MIPI, so that means that's 8, 9, 10. So you technically could have 8 cameras, with 1 megapixel connected to the system, and we just need 6. So there is some room, there's some bandwidth, for further processing. It has image signal processing. It's got all the features that is optimized for computer vision. So it really makes the decision to select a computing processor like this pretty straightforward. It's got some other capabilities because it's an automotive processor. It's got things like Ethernet and certain protocols that are very specific to the automobile world. But for the most part, this is what we're looking for: the image processing capabilities and the CPU itself, which can have 2 Cortex A53 processors, and it has 1 Cortex M4. So it's got a lot of computing power in here. And it has a 3D GPU if you want to connect a display driver to it, a display device to it. And it also has, I believe it has a DSI, MIPI DSI for the output of the display as well, if I'm not mistaken. Yeah, so that's why we have selected this processor. And let's go about and see how we're going to design it. So NXP generally gives you the evaluation board of how you can go about designing a custom board. And this is the board where they've given us the design and the schematic. So we're going to walk through the design and the schematic and see what we need from this, because a development board generally showcases all the capabilities and features of the processor, which we may not necessarily need. As I mentioned, this is an automobile focused processor, and we're trying to use this mostly for a drone application. So all the capabilities that might be necessary to work in an automobile setting, we may not need. So we can definitely distill down these connections and the peripheral devices to something that we just want. All right, so let's go have a look at the processor itself. Okay, here we go. So this is the schematic. the high-level schematic of this particular board that we have over here. And what does this board really have, right? Like, so what are we really testing out? So it's got two flex ray ports, which I think we would not need this. I think it's optimized. It's a protocol that they use, I think, in mostly in the automobile world. eMMC flash, which is solid state peripheral memories. These are hard drives, you can also call them. And basically, they store permanently. They can have. It's not like DDR, which is a read access memory. So you have the capability of having 16 GB of DDR. So that's a lot of memory for computation, which you would need because you're going to get all the images from the cameras, and that's going to consume a lot of bandwidth, and you would need a lot of memory just for the computation of calculating the depth, stitching the images, figuring out how to navigate the whole drone. So you would need a lot of memory, that's a good thing about this processor, that it can handle that. 2 SD card interface, Spi interface, HDMI connection if you want to connect a display port, a PCI Express board, connection, a compass, which is an IMU, which you can connect an accelerometer, a gyroscope, or a magnetometer. So this is basically a magnetometer. 4 camera ports, and here we're looking at the 2 MIPI CSI ports and the 2 parallel ports, not just a serial, but even the parallel. Then you got 1 gigabit and 6 automotive Ethernet ports. As I mentioned, this is for automotive purposes, so we're not going to really use this. Expansion connections, 2 LIN ports, again mostly automobile. JTAG and trace is good for debugging the board itself. So yeah, HyperFlash and SPI and RFlash, again, these are all memories which you can store data onto, or you want to store an operating system. In this case, you would have to store it in in an HyperFlash or an RFlash, or even in an eMMC. All right, so let's go about and see what we're really designing. Now, the circuitry looks a little complicated, but in reality, when we're designing a board like this, now this, mind you, this board has been designed in 2016, 2017, and in the span of 4 or 5 years, there are better components that we can select. So we're also going to look at how we're going to make this board based on today's components, because here what they have is the power delivery for any of these highly computational processors is quite complex, because powering this processor requires different voltages for different parts of the processor to function properly, and that's why the second page which we have over here is the power delivery network, which is nothing but how are you going to deliver power to this processor. And you have different voltages for different parts of the processor. So you have 5 volts, 3.3 volts, you need 1.2 volts, 1 volt, and that's just the voltage. And then you also need to calculate how much current that's going to consume, which is basically the power that these things can handle. And all of that is given in the sheet over here, as you can see. So it says 12 volts is nominal voltage. It's consuming 2.6 watts. The current amperes is 0.224. The main thing is over here, the one voltage over here, it's consuming 10 watts, which means it's consuming 10 amps. 1.2 is also consuming a lot of amperes. So the different voltages correspond to different parts of the processor and the amount of current that they're consuming. So it is a highly, it is a powerful processor and it's doing a lot of computation, so it is going to be hungry for power. So this is the power part. We will be using a different circuitry for this, and I'll get back to you on the power. But let's brief through the schematics so that we can go about in designing how it should work. And once you have designed the power, so you've given 12 volts, and then from 12 volts you want to buck that voltage into different voltage levels. So that's what that circuitry does, and then you feed that voltage into the different parts of the processor. So in this case, these pins would require 1.35 volts, which is the DDR memory. Then certain pins, the core part would require 1 volt. The other parts of the processor would require 1.8 volt, 3.3 volts. So you're basically distributing the power to the processor based on the voltage requirements, the voltage level requirements, and the power requirements. All right, so then we move to the third part where you have the compass and the magnetometer. Now, when we design this board, the thing is, every processor has even a microcontroller would have a couple of pins, and each pin can be multiplexed to have different capabilities. So for example, let me open up the multiplexing sheet and this particular board allows you to basically multiplex every pin into all the possible functionalities and features. So when we look at the schematic over here, you're looking at, hey, we're connecting the IPL and the VIU, which is the image processing part of the pin, and you're basically multiplexing it and saying, hey, do you want to use it as an IPL or you want to use it as a VIU, which is the which is the parallel camera interface, or you want to use it for the IPL connector. So that same pin is multiplexed into, you can use it as different features. And this schematic has a lot of this type of circuitry, which allows you to use both the functionalities, because the same pin can function as both, provided you can control it through the software. And then from the software, you can basically say, you want to use it as a camera interface, or you want to use it as something else. So in our schematic, as of now, we won't be using this IPL connector. We'll be using mostly it for as using this pin as purely for one functionality, which is the camera interface. All right, yeah. This is the DDR3 memory layout. This is, it's pretty standard. A lot of it is connecting the pins to the right pins, and powering the memory. All right. NOR flash, hyper flash, CAN. This is all about basically hard disks, in simple in the simplest terms. So you can have it as eMMC, you can have it as a Wi-Fi SD card and a micro SD card. So in this particular case, I think the way we're going to minimally design it, we're probably going to just use it as an SD card, and maybe in the future designs we'll add the MMC and the NOR flash. Because as of now, we're just trying to get the board get started. We won't be using HDMI in the immediate design. We won't be using HDMI and LVDA. So our immediate design, to give context, is this is what we're basically trying to do is whoopsie. What went wrong over there? So our immediate design, we're trying to make the bare minimum setup is to just power the board and get it working, and then connect the cameras if possible. So we're gonna segregate the external power supply, and we're going to talk a little bit about it, and then we're going to power the board, and we're going to basically boot from the SD card. The SD card will have the Linux image. We basically stored the Linux image in this SD card. It's going to have 4 DDR3 memories as per the schematic, so we'll use that as a reference layout, which we have in here, and based on the development board. We'll have the JTAG interface so that we can debug and troubleshoot and see if there's any runtime execution that we want to monitor. It's always good to have some testing ports. We'll have the capability of resetting the MCU. We'll have the camera CSI, because we're using this for the camera, so it makes sense to basically test the camera and interface as quickly as possible. And then we have UART, so that we can access the board through the terminal. So UART through USB to UART is one of the videos. That's the reason why we created the USB to UART, because when it comes to interfacing with the processor, UART, you can use the terminal, and you can do that by converting the USB signal into UART, and the USB can be connected to your laptop. So this is the bare minimum setup that we're going to do, that we want to design first. And yes, the schematic has got lots of capabilities, because it's trying to utilize all the functions and features of the board and of the processor, but we don't need all of that, because we're just trying to test something quickly and rapidly prototype so that we can move forward. All right. So what I've done over here is, I don't want to go through this whole schematic, but basically we'll go through the one that we have designed so far. Is we've taken the power circuit right from the NXP schematic, which is important, because they've literally laid it out, and there's nothing we can really change, because that's the power to the processor. I've even copied the DDR memory layout, because again, it's pretty straightforward. It's just literally pin-to-pin mapping, and you don't want to hand do this, because if someone has done it, I would just copy it, because a mistake over here can cause problems, especially if you make a mistake with one, if the pin is assigned to the wrong pin. That can be catastrophic, in the sense your memory might not work. So to minimize errors, it's better to just use what's already been designed. And here comes the more of the modification, in the sense that the MCU memory interface, we're going to use the memory purely through the micro SD card socket. So we're just going to use, because this particular memory can be multiplexed into the NOR flash, eMMC, SD card, and here we're just probably, and we're not probably, we are using it purely for as the SD card functionality. The UART to USB, because we already created as an external board, all we got to do is basically feed it into a small little header over here that'll connect to the USB to UART breakout board that we have designed, and then we can connect this to the computer. This part of the JTAG, which is you can connect this to a JTAG probe, and then you can debug runtime execution, runtime of the software running in the processor. Then we have the reset circuitry. So if something goes wrong and you want to reset the circuitry, we would like to just press a couple of buttons, a soft reset, and then there's a power on reset. That's what the POR reset is. And when we reset, we want to make sure that the boot mode is booting from the A53 core, and we also wanted to boot from the SD card. So this is some of the configuration. I'm not confident that this part of the schematic is right. I have sent the schematic for validation to the manufacturer, and we'll get a response and see if this could work. And the last part of the schematic is the camera interface. So we'll have two pins for connecting the MIPI CSI interface, and people call it the MIPI. I just like to call it the MIPI. And here we have the parallel digital camera interface. So you can convert the parallel digital into you can convert a CSI based camera into a parallel using some form of converter, and vice versa. But in overall, we have the capability of using the processor for all its camera capabilities or this camera input. So we want the schematic to be there, and that's what we have. And then when we're using MIPI or CSI MIPI for the camera interface, you would want to have the I2C data, because that's how you communicate with the MIPI protocol in controlling certain features of the camera. So that's why we have this particular part of the schematic. Yeah, that's what we've done. We've really made it extremely simple, in the sense that I won't say simple, but at least we try to simplify the original complex evaluation board into things that we just purely need for the features that we for what we want to test the processor for, which is literally camera. But to get the camera working, we would have to install Linux into the system. Then we would like you to play around and see how the system works. Then we would like to capture the videos from the cameras and do some basic processing by utilizing some of the capabilities of the processor, and and take it from there. All right. So this is what we have over here. So let's focus on the external power right now, because this is we need the external power in order to power the NXP S32. And power is generally is one of the subjects where it seems it seems like it's not necessary to focus on, but it's in the sense that you feel like why don't we just copy the schematic that's already out there. But I generally feel like what they've designed was really using components that have been that they've used 6-7 years ago, 5-6 years ago, and I think we can use better components. And NXP itself has created its own power factor IC, power management IC. So let's have a look at the application note that NXP has provided. I believe I have it over here. This is not it. Yeah. So when we so this is the application note that NXP has provided for the S32V234, and it basically tells us what is the requirement of the S32V234, and it's pretty well designed over here. And all it says is that why don't you use the PF8200, which is an NXP power management IC. And the reason why you want to use this power management IC, because it will deliver, this one IC will help you deliver the required power in terms of voltage and current to the necessary parts of the S32V234, which is a good thing, because we will be able to save cost and even design complexity than this board over here, which has a couple of MOSFETs just to buck the voltage from 12 volts to 5 volts or 12 volts to 3.3 volts, and and there's a lot of this switching going on. And if you can have an IC that can do a lot of this internally, which is what NXP proposes over here with using their PF8200, is really what we're going to do, and this is what we're going to use. So one of the next videos we'll be talking about the power factor delivery of the board, and we'll start to design the power factory. And in one of the next videos we start to design even the schematic and the PCB for this particular board. And we want to get this shipped as soon as possible so that we can start testing the board and the camera interface hopefully by next month. Alrighty. And thank you all. I mean, if you really like to see, the way we're progressing, our updates, and some of the things that we're building that could really help you as well, highly recommend you subscribe to this video. And until then, and until the next video, we wish you all the luck. Thank you.